Look.
Probably.
It was page 85.
Page 85?
Yeah, this one was on the homework, and I just had trouble with symmetry.
85, and which number?
Reflexivity, rather. 15.
Number 15, okay. Yeah, I'll in a moment, I'll look. Maybe I have something here. You guys have your finals? All of you? So I don't need to look. Your finals. Okay.
Midterms, yeah.
Not midterms. Okay, so let me put it all back, otherwise you see I already lost one of them. Okay, let me answer the question then. Wait. Now 15, yeah? You told 15?
Yeah, I got.
Okay, so we have alpha and beta, and we say that they're related if they're conjugate. Show that it's equivalence relation. Was the homework or just?
Yeah.
But
I did most of it, I just couldn't
okay, very much. So you say that these are related. What is it written if alpha or beta? Is beta is equal to sigma of the sigma inverse, yeah? Something like this. Okay. Why is it equivalence relation? So it's usual story. I'll give later. Usual story. You have to check that alpha is related to alpha, and then if then, and finally if alpha is related to beta, beta is related to gamma, then alpha is related to gamma, right? Okay. Why alpha is related to alpha? Can you find a sigma such that you can write alpha as sigma alpha sigma inverse? How about identity? You don't like identity? Take alpha. You know? Would you agree with me that alpha inverse is equal to alpha? Yeah. Don't like alpha, take alpha in power 10, you know. Anything which commutes with alpha. Okay? So identity, I think, actually is the perfect choice. Now, this is given for iffy part. Then, of course, you can unstrip it and write sigma inverse beta sigma is equal to alpha. And this is as good, you know, just call sigma inverse tau, you have tau, beta, tau inverse, right? And this one is also quite easy because here beta is equal, say, to sigma alpha sigma inverse, gamma is equal to tau beta tau inverse. So if you now plug it in here, you will get tau, sigma, now tau beta tau inverse, sigma inverse, right? But of course, if you now bracket it like this, then you will notice that you have sigma tau beta sigma tau inverted. Same story. So that's quite easy. Okay, any other questions?
Page 84, is it?
Yeah,
Revive?
Okay. Any other questions? Any other questions? Questions? No more questions. Okay. So what are we doing with you now? We started with you a new chapter, right?
Yeah.
Chapter about groups. Yeah. Now we actually learned with you a lot of notions when we were learning ring theory, which will come handy now and we understand. So let me again, since we had a break and forgot everything, what is a group? Group is a set with operation, which traditionally is denoted by multiplication. Again, there is a tradition that if there is some additional condition, then operation is written as plus as addition, but in general, yeah. With this operation, of course, if you take two elements from here, then this operation also gives elements from the group, so closure, of course. And then this operation is associative. There is a special element called identity, such that both these products will give you A, and for every element there exists a reciprocal, traditionally denoted as A inverse, such that these both products are identical. So whenever you have this situation, it's called a group. The best, in a sense, in sort of universal example of groups is a bijection. Bijection. If you have a set and you consider all bijections of the set to itself, then you have composition for bijections, and these bijections with composition as an operation constitute a group. Well, let's check. So I have a set S, and I have all bijections from S to S. So, of course, composition of two bijections, as we know, is a bijection. So we have closure. Composition of any functions, bijection included, is associated. No problem. There is identity. What is identity? It's bijection which puts every element to itself, right? Then, of course, this is both composition. And for a bijection, you know, there is an inverse bijection. You can invert. One-to-one function is invertible, so bijection is one-to-one function. And then, of course, these both compositions are identity functions. Send every element to itself. And in a sense, any group can be thought about as a subgroup of all possible bijections of some set. And we will see it later, maybe, I don't know. Now, what is a subgroup? Can anybody just give me definition of a subgroup? What kind of a subset is reasonable to call subgroup? All the properties are induced. Don't worry about it, because when we're talking in this context, we take subset. These are the same iterations. We're not inventing new iterations, because otherwise the structures won't be related. It doesn't make sense. So the only thing which you have to check, that there is closure. If you take two elements from this subset and multiply them, the result is also in this subset. For any element, inverse is also in this subset. You also can check that identity is there, but it follows, because if you have an element, then by closure condition, inverse is there, and their product is identical. Or you can play the same trick as I'm sure some of you played with linear algebra. Instead of requiring that sum of the vectors is there, did you discuss this possibility to tell the difference of the vectors is there? Did you talk about it? No? Okay, never mind. So let me give you a different definition of a subgroup. So I have a group G, and I have this subset, say H, and I want it to be a subgroup. I claim that what is enough to check? Two things, well, actually, that H is not empty. Because if it's empty, that's not interesting, right? And if I have two elements in H, then instead of checking that this product is there and inverse, just check, require that this is also there. So if this is true, then this is true. In this case, H is a subgroup. It's kind of fun exercise. So suppose we have just this. So what I should deduce? That if I take two elements, then product is there, right? Well, let's do it in a stride. H is not empty, right? So there is an element K or whatever. There is an element H and H. Since otherwise it would be empty. And I assume that it's not empty. So there exists an element in H. Then by this property, element H multiply H inverse is also there. And this is identity. So identity is also in H. Because that's required, right? Okay. Now suppose I also have element K in H. Then I can, you know what? I forgot to prove. So I have this, right? So identity, so what is in H? H is in H, E is in H. I forgot to check. Then H inverse, which is equal to E, multiply H inverse. Again, by this property is in H, right? Because if E is in H and H is in H, then E, H inverse required to be in H. So if I have element H in H, then identity is there and H inverse is there. Okay, very good. But
Yeah, it's good.
okay. So now I have element K. By what we just showed, with the same implication, it implies that K inverse is in H. And then H multiply K inverse inverted is also in H. But of course, K inverse inverted is K, right? It's clear that K inverted and then inverted again gives me K again. So this is HK. So it's kind of fun. Instead of checking several properties, of course, computationally it doesn't make any difference. You can check just then whenever two elements are in the subset. If it implies that this ratio is in the subset, then it's a subgroup. So, but anyway, subgroup is a subset which is relative to induced operations, because there is this operations here, well, whatever operation in inverting on a larger group, which is ambient. So that's called a subgroup, and I will be using this notation for. That's to stress it. It's not just any subset, but subgroup. Okay. So that's the notion of subgroup. Notion of subgroup. Very good. Okay. Now we have a lot of examples of groups. Say if we consider integers relative to addition, or any Zn relative to addition, or all real numbers with exception of 0 relative to multiplication, or all complex numbers with exception of 0 relative to multiplication, or all complex numbers which are equal to 1 by module of complex numbers is 1. You know these complex numbers which live on unit circle. They also constitute a group relative to multiplication. Or just two numbers, just two real numbers, 1 and -1. They also constitute a group of relative to multiplication. Or any roots of unity on complex plane. Say roots of degree 10. They also constitute a group, right? Because if you multiply two roots of 10, degree 10, when you raise them in power 10, you will get 1 back. So you have a lot of different examples. Well, all these examples which are mentioned were also commutative, where this operation has additional property, A multiply B is equal to B multiply A. Groups like this, for some historical reasons, are not called commutative groups. We were using word commutative rings, right? They're called abelian groups in honor of a guy named Abel, who was first to look at objects like this and systematically use them. Okay. So abelian groups is when operation is also commutative, which generally speaking is not required. Okay. First interesting example of a group will be all permutations of set of 3 elements. We can think about it geometrically as the following. Take a regular triangle in which all sides are equal and all angles are equal, and consider all possible symmetries of this triangle. So there are exactly 6 of them. You can identical, you can turn it, right? You can turn it twice. So we have identity, and let me call turn A, and then you can square it, and if you cube it, you will come again to identity. And you have symmetries. Take, say, symmetry like this, or symmetry like this, or symmetry like this. That's it. There are no other things. Actually, if you just look at all possible bijections of a set of size 3, it's easy to figure out that there is exactly 6 of them, right? Because if you take size 3 set and you map it into itself, then first element, you just number them, 1, 2, 3, right? Well, it's like permutations, which we discussed with you. 1 can go to any. It has 3 choices, right? Then 2 can go to any which is not occupied by 1 yet. So just 2 choices. And the last one doesn't have any choice, it must go to the last one. So that's why you have 6 of them. So you also have this, symmetry, and of course if you take one of the symmetries, then if you look at compositions, you will get another symmetry. Okay. So just to, for warm up, let's discuss with you the following. Let's try to describe all possible groups of size 6. Well, let's start even before? Well, all possible groups of size 1, it's not very interesting, right? Just identity element, that's it. It's certainly a group, yeah, because product of two identities. How about two elements? If you have two elements, well, by requirement, you must have identity element in the group, and you have another, so this is a group of size 2, and another element. Then, of course, what is E multiply E, we know. What is E multiply G or G multiply E, we also know, it is G. So what we don't know, what is G multiply G? So what G multiply G can be? It can be only E. Why? Because what is our choice? This is all our group. It's either E or G. What will happen if G multiply G is G?
G is E.
G is E, because you can, in the group for G, you have inverse element, right? You can multiply by inverse element, you don't care what it is, and then you will get that G is equal to E. And if G is not equal to E, then it's impossible. So G is inverse to itself, right? G squared is A. That's it. How about size 3? Size 3. Okay, well, we have E, we have G, we have H. Then we have to look at different possibilities, right? Well, of course, product by E we know. So G squared we already know, it cannot be G. G squared cannot be G. So what it can be? Either H or identity, right? Maybe H, maybe identity, we don't know. Same story with H squared, in a sense. Yeah, we also don't know. It's either, it cannot be H, it's either G or identity. So, is everything possible, or some restrictions? Well, I think that would be the best case scenario if G squared is equal to H, because then everything is expressed from one element. So, because then we don't have much choice. You immediately deduce that G cubed must be identity in this situation. Why? Because if it's G, then G squared is identity. If it is G squared, then G is identity. Well, it's there. Okay, so that would be easy. Okay, now well, let's look at more complicated case. Suppose in this situation, G squared is equal to identity. Okay, let's think. What can we say then? So now, about these two elements, we know everything, right? E and G, actually, they constitute a subgroup, right? Because this subset. So what about H? Well, we have H. Which elements we have to determine? We have to determine what is, say, G multiply H. That's what is important. Now, what G multiply H can be? Identity. No. Why GH cannot be identity?
H to be G.
Because H and G are different, right? G by G is identity, so this is not identity. Can it be G? Can this product be G?
No, then H would be identity.
Then H identity. So it's not G also. Can it be H?
Then G would be identity.
Then, okay. So we're in a pickle. If we assume that G squared is identity, then G multiply H cannot be anything. So impossible. So that's the only version. And today we discuss something which will actually help us to understand why it was completely clear that we have nothing else. So maybe I was jumping a train. So let me discuss with you some rather obvious thing which will help us greatly to describe what I want to do. All groups of size 4, all groups of size 5, and all groups of size 6. You know, of course we can try to do something similar and we'll succeed. But why not to prove some general fact which will help us? Now, here is the general fact which I want to discuss. It has even a special name. It's called Lagrange theorem. And the theorem is like this. Suppose that size of G is some finite number. It's for finite groups. It can be formulated for infinite group, but in the way we're going to use it. Then suppose H is a subgroup of G. Well, I'll write it in some fancy way just to, show your memory. Then N is equal to 0 mod size H. So what I'm trying to say in more pedestrian terms, size of them. The size of a subgroup is always divisor of size of a group. Divide size of a group. Okay. That would be really neat, because then for size 3 group we won't have any choice immediately, because what was our bad case scenario? When E and G constitute a subgroup of size 2. But since 2 doesn't divide 3, that would be impossible. So how to prove this thing? Well, actually we had some experience with things like this, but just maybe it's hard for us to associate it. What I will do, I will introduce some equivalence relation on group G. Some relation I introduce, it will turn out to be equivalence relation. So it will cut it on non-overlapping classes. Every class will have the same size of H. Then we will prove it, right? Because if G is cut on non-overlapping classes, each class is of size H, then it exactly means that size of H divides size of G. Agreed? Okay. So what would be equivalence relation? I would say that two elements of G are related if and only if this ratio belongs to H. Well, I probably shouldn't use word ratio because, or I should use, say, right ratio, because we have two ratios here, left ratio, right ratio. So anyway, if this, so let's check that this is equivalence relation. Now what is important here? That H is a subgroup. Otherwise, if it will be just any subset, it won't work. So why is it equivalence relation? So first of all, why G is related to G? Well, it's because G by G inverse is identity, and identity belongs to any subgroup. So reflexivity is there. How about symmetry? If G1, G2 are related, then G2 and G1 related. Well, what this means, that G1, G2 inverse is an H. So if this is true, then what we want to deduce? That G2, G1 inverse is an H. So this is given, this is question mark. So now, why the fact that this is an H implies that this is an H? What is the product of these two guys? This multiplied by this. What it will be?
E.
Identity, right? So this is inverse of this. But of course, if this element is an H, then inverse to it also must be an H. Right? H was a subgroup. So if it contains an element, it must contain an inverse element. Otherwise, it's not a subgroup. Yes? And finally, too iffy, yeah? If G1 and G2 are related, G2 and G3 are related, then G1 and G3 are related. So let's write more carefully here what's going on. So G1 and G2 are related. It means that what? G1, G2 inverse is an H. G2 and G3 are related, so help me write what it means. G2 and G3 are related, it means that G2, G3 inverse is an H, right? Correct? So that's what these two assumptions mean, correct? What are we interested in? G1, G3 inverse, right? Which is of course equal to G1, G2 inverse multiply G2, G3 inverse. See, our operation is associative, so there is no need for me to put any brackets anywhere. So that's it. So this is equivalence relation. Okay? Great. So now we know that different classes don't overlap. because it's equivalence relation. So my concern is now to just say somehow that size of each class is exactly size of H. After I prove it, I prove this here. There, this one. Okay. So, take all elements like this. So, what I suggested to be, so G1 and G2 are related, is the same as G1, G2 inverse belongs to H. Let me rewrite it a little bit again. Let me write it like this. It's equivalent to the fact that G1 belongs to H multiply G2, right? Oh, because what this means, that there is some element H here such that G1, G2 inverse is equal to this little h, or the same as G1 is equal to H G2, right? Okay. So what I'm trying to say is that class of G1 is exactly H G2. Now, I didn't prove it, so let me put a question mark. But if I prove it, we're done. Because, of course, this class contains exactly the same number of elements as an H. Right? We're in a group, so different elements from H multiplied by G2 are different elements. So, okay. Okay, so that's what we want. Now, so let's check both directions. So, suppose I have an element G, which belongs to H G2, which is the same as to say that G can be written as H multiplied G2, where H is an H, right? Then, let's look at G1 multiply G inverse to check that they're in the same class, right? G1 multiply G inverse will be, oh, you know, what I'm doing here. Class of G is equal to H3. I'm sorry. Yeah, I know. Did I tell you that mathematicians are famous for saying one thing, writing another thing, and thinking something else, you know? So that's the case. Okay. So that's, I took some element here. Now, this element I can call G1. So G1 is HG, where H is. And now I'm writing what is class of G, right? What is G? G1 inverse. It will be G, H, G inverted, right? But you remember, oh, by the way, do you remember this? I'm sure you discussed it in your algebra, that AB inverse is not equal to A inverse B inverse. It's equal to B inverse A inverse, right? And it's easy to check, because if you take AB and multiply it by B inverse A inverse, on this side or on the other side, you will get identical. So this is G, G inverse, H inverse, right? G and G inverse will cancel out. H was an H inverse is an H. So it is an H. So every element from this set, so what did we prove? That if we take element from this set, it's equivalent to G. So class of G contains HG. Okay? Now I have to check another thing, right? I'm taking now G1, which is related to G. I somehow should show that G1 belongs to G. So G1 is related to G. What it means? That G1, G inverse belongs to H. It means that G1 indeed can be written as some element H from here multiply G. Oh, so we're done now. That's this class. So now what do we have? That whenever we have a group, we have a subgroup, we can introduce this equivalence relation. It gives us equivalence classes. Each equivalence class is of size H. There is so many there. And so if situation, if it doesn't matter here, by the way, is G finite or infinite, you understand it? Doesn't really matter. But if G is finite, it means that it's cut on several pieces of the same size. Each size is of size H. So indeed, H divides G. So size of H in this situation, right? This subgroup divides size of G. Okay. So with this theorem under the belt, let's proceed with our attempts to classify groups of small size.
How important do you think that all was?
This is important. That's a very... Okay, now, how important is learning about groups? Is it of any importance?
I don't know.
You don't know. Okay, now, well, it is important for you personally because you want to pass the course. But also, groups are really very, very important fact, very important notion. It's, for example, modern physics without group theory would be completely impossible. Classification of elementary particles really breaks through with classification when people understood that it's some questions about groups. So they're not only important in mathematics per se. If you want to understand how universe ticks, you need to know group theory. So this is important from this point of view. Have some notion. Now, groups are described. Now, another thing, say, aesthetical point. You know there are some parquets. Well, this is very primitive one, right? Did you see any elaborate parquet? When this floor is tiled by some, something beautiful. All of these beautiful things have some symmetries. And in a sense, human notion of beauty is very much related to notion of symmetries. And symmetries are described by groups. How is that for important thing? Is it important? Okay. Now, I mentioned many times already in this course that for polynomials of degree 5, there is no formula for roots. Did I talk about it? In order to prove it, you need groups. In order to research completely question about when polynomials have roots which are expressible, and you need to have very well developed groups here. Also, groups are extremely important in mathematics, not just for their sake, but in all branches of mathematics, practically in all branches of mathematics, groups play very, very important role. So this is one of the really very basic and fundamental objects. So attempts to learn more about it are not wasted.
Okay, can we maybe do a brief overview of what we did here?
Overview of this last theorem?
Yeah.
Okay, because you were a little bit switched off. Okay.
I got lost.
So here is what we're trying to prove. If you have a finite group and it has a subgroup, then size of a subgroup must divide size of a group. That's kind of a statement. It's not obvious out of general principles, out of just this definition. That's what we were trying to prove. And how we proved it? We introduced some relation on group G. Two elements of group G are related if this expression G1, G2 inverse belong to this subgroup H. That's some relation, right? Because for some products like this, it belongs to H, for some not. We showed that this is an equivalence relation by just checking all three properties of relation to make it equivalent, right? To make it equivalence relation. Okay? Then we used what we learned about equivalence relations, namely that classes of equivalence don't overlap. You remember it? That's what's specific of why it is important to show about a relation that's equivalence relation, if it is, of course. We cannot show it if it isn't, but if some relation is equivalence relation, then different classes don't overlap. If two classes intersect, then they coincide. Remember it or not? That's a basic property. That's why we introduced equivalence relations. That's why we discussed them. But that's the basic property of equivalence relations, and I'm not going to repeat it. You want to learn it again from me? Come during my office hours and discuss it with me, okay? When are my office hours?
Thursdays.
Very good, okay.
3:30
Yeah.
is when
No.
they start. 4:20.
Something, well, find it, it's written on syllabus. Okay. So, after that, we show that every equivalence class in this situation has exactly the same size as size of this subgroup H. And then it's exactly what I'm trying to prove, because if these classes don't overlap, we took J, with this group, okay, think about it as a blob. We cut it on pieces. Each piece has a size h, right? So all size is something with factor size h. So size of h divides. Okay? So that's very simple theorem. Well, maybe it's not your perception. In fact, it is. And I don't know, it's certainly somewhere there. We will find it at some point in your, yeah. But what I want, why I proved it, because I had this idea to think about examples of group, sort of describing all groups of small size, and this certainly will help me very much. So size 1 we discussed, size 2 we discussed, size 3 we can discuss again, because now size 3 is very easy, because 3 is prime, so it doesn't have any subgroups, right? Of course, it always has identity as a subgroup. It always has itself as a subgroup, but it cannot have any intermediate subgroups. If we talk about, maybe we can talk about proper subgroups, maybe in this context also, right? Any subgroup which is not one of these two trivial cases. So since 3 is not divisible, and then of course it immediately follows that if I take E and G, then G squared cannot be identity in this, because if size of group is G, because then this would be a subgroup, and size of this subgroup is 2, right? And 2 doesn't divide 3, so that's the only possibility. By the way, this group, as well as previous two groups, are abelian. Once again, what does it mean, abelian? Product doesn't depend on order. Now let's look at groups of size 4. So I have E and I have element G. Now, if I assume that G squared is identity, I don't get any contradiction. Because I have a subgroup of size 2 in a group of size 4, and 2 happily divides 4. So no contradiction here. So that's certainly an option. Okay. If we start with this, suppose that's also, yeah. Then I can take next element H, and then my group must contain elements GH. And from our previous discussions, I think all of us understand that GH is not identity, right? Because H is not equal to G, right? It is not G, because then H would be equal to identity. It's not H, because then G is. So that's our fourth element. This is our fourth element. Okay, now, so what we know now? We know that G multiply HH is this element. We know that G multiply GH, because G squared is this element. So this we know. But we don't know what is G, what is H multiply H. We don't know. And we don't know what is GH multiplied by G on the other side. So that's, we don't have it. So what is H squared? What is H squared? What is H squared? What are choices possible? It cannot be H, right? We know. Cannot be GH? Also no, because if it's GH, I cancel, and then H is equal to G. So options which I have is either E or G. That's my options. Well, if H squared is identity, I can look what is going on, and then say let's look at this case. And H squared is also identity. And H squared is also identity. Okay, then I know, since everything, I don't know one element. Which element I don't know? Opposite order. HG, I don't know. It must be somewhere there, and I don't know what it is yet. I have to decide what it is. What is HG? It cannot be identity, right? Because H and G are different. It cannot be G, it cannot be H. I don't have any choice. It must be equal to GH. Now I know everything. All products, I know everything is okay. Right? And what is also interesting, what would be HG squared in this situation? What do you think? What is hg squared for this group? Remember, g squared is identity, h squared is identity. What is hg squared? Identity, right, because it's hg, but because of that you can switch the order and you have h squared by g squared. Identity. So it's kind of curious. We have identity element and three elements, square of which is identity. It's a group, okay. Another case would be when h squared is not identity, but g. If h squared is g, then that's really neat, because then I can write here that it is h squared, and g multiply h is h cubed. And then if I look at h in power 4, my only choice would be to make it e. Why so? Because if I look at h in power 4 and it is h, then h cubed is identity. If it's h squared, right, then h squared is identity. If it's h cubed, then h is identity. Well, the same group as for Z4 with addition, right? If you look at group Z4 with addition, you will get exactly the same kind of group, right? 4 elements, everything generated by one element. What is generating element in Z4 for addition?
1.
1. Of course, 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and 4 times it's 0. That's it, and 0 is neutral element. Aha. So I deduced it assuming that g squared is e. But what was other option? G squared is h. But then we'll have exactly the same situation, just with g which is generated. Okay. Size 5 is not interesting. Why size 5 is not interesting? Same story, prime number, no subgroups, right? So now, how to create a subgroup in a group? The easiest way. Take any group, pick an element g, and consider e, g in power plus or minus 1, g in power plus or minus 2, and so on. All things like this. They certainly will constitute a subgroup, right? When you multiply two guys like this, like g in power I by g in power j, result is g in power I plus j. Okay. Well, if you take subgroup of size 5, or group of size 5, or for this matter, of any prime size, take any non-identity element and consider all its powers. It must be all group because it doesn't have proper subgroups. So then what I will have? I will have e, g squared, g cubed, okay, g in power 4, 5 elements, and then I don't have any choice. G in power 5 must be identity. Again, some simple groups. All these groups are called cyclic groups. Again, for some historic reason, they're called cyclic groups. Oh, they are all generated by one element. So it's not interesting. So first interesting case is groups of size 6. In what sense are they interesting? There are two groups of size 6. One is cyclic, namely e, g squared, g cubed, g4, g in power 5, and then g in power 6 is identity. And the other is non-abelian. And this is exactly symmetries of this triangle, which I erased. It turns out that there are no other groups of size 6. But why it is interesting? It's the first size where you have non-abelian group. For all smaller sizes, groups are necessarily abelian. What is interesting, if I go further, size 7 is again necessarily abelian, because 7 is prime. With size 8, it's more complicated. There are non-abelian examples, but we're not going to go this far. So I will classify with your help all groups of size 6, and this line of thought we will drop for a while. I'm not going to discuss groups of larger size in this course. Okay. So size of group is 6. So what can be? I think we talked about it, but maybe it's a new word for us again. What can be orders of element? What are orders of element in a group?
Number of times you raise it to get back to the cell. Or
Oh.
one.
To 1. Okay, so if I pick an element G in G, then as we discussed, identity G square, and so on, if I take them all together, they constitute a group. Well, why? I don't need negative degrees. Because it's a finite group, as we discussed with you. There are two different i's and j's such that j in power I is equal to a j in power j, because I cannot have infinitely many elements sitting in a group of size. But this, of course, immediately means that identity is equal to j in power j h minus I, so, yeah, j minus I. And so it has finite order, and then elements, if I have the smallest difference here, the smallest number, such that so d is order of g, that means that g in power d is identity. D is the smallest. Okay, that's what is order. Then, of course, elements identity g in power d minus 1 is a subgroup, constitute a subgroup in our group G. It doesn't matter whether size of group G is 6 or whatever. But then we know size of this, how many elements here? I have D, right? So in our context, D must divide 6. So what are numbers which divide 6? 1, 2, 3, and 6, right? So these are all possible orders. Now, 1 is very boring order because there is just one element of order 1, identity. Okay. If I have an element of order 6, I'm also done. Because then I take this element, and its powers generate all group. And then, of course, it's clear how multiplication works, right? J in power I multiply J in power j is J in power I plus j. Okay, and of course, it doesn't depend on order, because in the last count, adding numbers, I plus j is equal to j plus I. So that will be a Abelian group. So it's not interesting. So I'm interested in elements of this order and this order. Okay, I have different options to consider. One option is the following. Suppose all elements are of order 2. So let's discuss this situation. All elements of G, of course, I throw away identity, have order 2. Let's think, is it possible that all elements of G have order 2? Well, let's start. I have identity, I have this element G of order 2, then I take another element H. Okay. Well, I also have element JH, right? It's group. It has order 2, right? GH squared is equal to identity. It's because of my assumption that every element has order 2. Well, but you know what? GH, it means that GH multiplies GH is identity, right? But you know what? If I take GH and multiply it by HG, it's also identity. Agreed? Because H squared is identity. So GH and HG are the same. Very good. So let's look at these 4 elements. They would constitute a subgroup. Right? Because square of every element is identity. And if I multiply G by H or H by G, I get this element. But say if I multiply G by GH, what it will be? G multiply GH. G squared by H, well, it's H. So it's closed under operation, it's a subgroup. Contradiction, why? 4 doesn't divide 6. Impossible. So I don't know much about this group, but I know there are elements of order 3. So there is at least one element of order 3. I'll call it A. I don't know, maybe all elements are of order 3. This I also probably have to look at, but right now, well, I'm happy that I found that there is an element A of order 3. So once again, you remember what I'm assuming? That it's not a cyclic group of size 6. Of course, in a group of size 6, there are elements of order 3, no problems. But this is not an interesting case, so I'm looking. That's kind of the largest one. Okay. So I have an element A and G, such that order of A is 3, which means that I don't know, but I know about 3 elements in my group. I have E, I have A, and I have A squared. And, of course, A cube is identity. Okay. Well, that's certainly not all. I have 6 elements. So let me take another element B, which is there. The moment I took element B, I have remaining elements. Why? Look at AB and A squared B. I submit that these elements are different from the elements which are written on the board. Well, let's check. Of course, these 3 elements are different. It's clear. These elements are also different because I took 3 different elements and multiplied by B. So, where can be equality? Well, can any of these elements be equal to one of these elements? That's my choice. That's the only possibility, yeah, to make a element. So, B is certainly not here, that's our choice. Now, can AB be one of the elements here? Well, if AB is identity, then B better be A squared, because A multiplied A squared is identity. If AB is A, then B better be identity. If AB is A squared, then A and B are equal. Impossible. Now, the same checking with A squared, no difference. If this is identity, then B is A, if A squared is A, right? Then AB is identity. Well, anyway, AB is identity means that B is A squared. And if this is equal, then B is identity. Okay, well, I have 6 different elements. Unfortunately, I know how to multiply these 3 elements, but I have not the focus how to multiply this. So, there is element B squared. What can it be? B squared. It's certainly none of these guys. Why so? Well, of course, B squared cannot be equal to B. Can B squared be equal to AB? No, because then B. Can it be equal to A squared B? Again, no, because then B is equal to A squared. So B squared is one of these elements. It can be identity, it can be A, it can be A squared. Well, suppose B squared is equal to A. Then I'm done. You know why? Because order of element B will be exactly 6. But also, what you see, if B squared is A, right? Then I can rewrite it. This will be E, this will be B squared, this will be B in power 4, this will be B, this will be B cubed, this will be B in power 5. Not interesting. It means that I have an element order 6, I assume I know. Same consideration for A squared. Suppose B squared is A squared. Why? You know, instead of doing it again, I will just say, let's call this element C. Then what is C squared? What is A in power 4?
A.
A. So, you know, it plays exactly the same role. I call it C, so I have E, C, C squared, B squared is equal to C. C has order 6. Not interesting. So the only possibility which remains to be considered is when B squared is equal to identity. That's the only interesting case. Okay. Well, I still don't know all of it, but at least I know what is B multiplied B. Now, if you think simultaneously about this triangle, then what would be A on this triangle? It is these rotations, right? And what is B such that B squared is identity? Of course, we don't know it yet, but that's kind of analogy, right? Any symmetry. Symmetry repeated twice is identity. Okay. So B squared is E. Okay, now what I don't know yet, I know everything about these elements. I don't know what is BA. Right? I don't know what is BA squared. That's my mysterious elements. Well, probably if I know what is BA, If I know what is BA, I will probably figure out what is BA squared. So what can be BA? Well, let's see what are options for BA. It must be one of these elements. So BA. BA. It is not identity, because then, if it's identity, B is A squared. It is not A, because then B is identity. It's not A squared, because then B is A. It is not B, because then A is identity. So it can be either AB or A squared B. That's my two options. I cannot have anything else for BA. Other four elements are impossible, right? So let's look at case by case. Suppose BA is equal to AB. Well, that's kind of familiar kind of relation. It means that they commute. Well, of course, in this case, I know what is BA squared. It's A squared B. Everything is okay. So now I have these elements, A. I already erased that A cube is identity. I have this element B such that B squared is identity. They also have BA, AB. Let's look at element AB. What is the order of this element? In which power should I raise it to get identity? Remember, orders can be, if it's identity element 1, this is certainly not identity element. It can be 2, it can be 3, it can be 6. That's my choices. Well, let's square it. Because elements commute, it is A squared by B squared. B squared is identity, so this is A squared. It's only because elements commute, otherwise I would be unable to write. What is AB cube? Again, because elements commute, it's A cube by B cube. A cube is identity, B cube is B, because B squared is identity. So what is the upshot? The only possibility is that order is 6. So in this situation, order of AB is 6, and we have an element of order 6. So we have a cyclic group. Not interesting. So my only interesting option is B squared is equal to A squared B. And of course, now my group is completely determined, right? Because I know how to rewrite any element, you know. I can, yeah, so what I don't know. BA is A squared B, then of course, what is BA squared? Well, it is BA, which is A squared B, multiplied by A, right? But BA, again, is, yeah, so it is A squared, so it's A in power 4, right? B. But A in power 4 is, so B squared is AB. So I know everything. And you know what? I don't need to check anything else. You know why? Because if I consider group of symmetries of triangle, or all permutations of set of size 3, it is non-abelian group. It certainly doesn't have an element of order 6. So some group exists. And since this is unique description, that must be that group. That's it. You understand? Because what I need to do, if I wouldn't know that such a group exists, I need to check that my operation is associative, right? Well, for every element, of course, there is inverse. But here I don't need to do it because I know that there is such a group. How do I know it? Because I know that all bijections of size 3 set constitute a non-abelian group of size 6. Why non-abelian? Well, it's very easy to check, if you will, that if I consider this permutation like this, 3 cycle, and symmetry, they don't commute. You remember the such notations? If I number them 1, 2, 3, I have cycle 1, 2, 3. What is this symmetry? This symmetry is cycle 2, 3, right? One stays put. Well, anybody can check that this guy, what is it I'm writing here? BA. Let me write it exactly like this. So BA 2, 3, 1, 2, 3 is equal to A squared B. Now, what is A squared? If this was A, then 1 goes to where? 1 goes to 2, and 2 goes to 3. If I square it, 1 goes where? right? And then I don't have any choice, 3 goes to 2, okay? Square of it, 2, 3, let's check that this equality is correct. I'm checking this one, right? Well, where 1 goes here? 1 goes to 2, right? And 2 goes to 3, so 1 goes to 3. Where 3 goes? To 1. 3 goes to 1, right? And then this doesn't happen. So that's what we have here. Then I don't have any choice. 2 goes to 2. Yeah, because. Okay. Now let's check this one. Where 1 goes? Nothing here to 3, right? Because this means. Where 3 goes? First goes to 2 and then goes to 1. The same thing. Okay. Now, if, and once again, it's a very important point, if I wouldn't know in advance with these considerations that such a group exists, my work won't be finished here. Because from this description, I have no the foggiest whether operation is associated. Right? And it would be quite a pain in the neck to check that it is associated. But since I have such a group, I know it is associated. The end of the story. Okay, so that's what we have. That's what we have. So now, I used with you all the time, and you didn't have any discomfort with it, cancellation property in group, right? Whenever I would ask you, is it possible that AB is equal to A squared, you would immediately yell no, because that will imply that B is equal to A. What you were using here? Cancellation property, right? Of course, it's in any group, no matter what the size. If you have GH is equal to GK, then H and K are equal, because you can cancel G on this side, and that's groups. Okay, definition of the group. Now, so that's first interesting example. First interesting example. They have a bunch of other examples. Look at section 1 and now, there is a very important example here, very important example. Groups like this play a very important role. It's the following, and that's, again, you know, I just want to remind you. Consider all matrices of size n by n. Some of them are invertible, some not, okay? You remember? Consider all invertible matrices of size n by n. Only invertible matrices. They constitute a group relative to multiplication. Okay, let's discuss it. Why it is now? Why it is important? It turns out that when you're researching groups, it's very important to have something like what we have here with this triangle. You already felt that. I was very happy that there is this triangle and there is this group acting on this triangle by symmetries of this triangle. It was very important for me. So there is this trick. It's called representation of a group. If you have a group, it is very neat when it's possible to represent it by linear transformations acting on a vector space. What does it mean? Take an element of your group and sort of force it to work on a vector space. Like I had a permutation of three elements, I force them to be a symmetry of this triangle. Similar thing. And so these things are called, it's called series representations. We're not going to talk about it. But this is something very important. That's why it's important for us to realize that this matrices constitute a group.